Hi there, and welcome from Ventura, California to today's virtual workshop, Autonomous Vehicle Safety, How to Test, How to Ensure. It's the second day of a two-day series sponsored by Spirent Communications, NovAtel, Inside GNSS, and Inside Unmanned Systems, and hosted by WebAttract. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we will be introducing our panel of thought leaders, as today's webinar is about hearing from these experts as they address the topic at hand. You'll also have the opportunity to have your questions answered at midpoint and at the end of the presentation during the Ask the Experts panel session with all three of our panelists. Now, we've invited you along with over 650 professionals across 50 countries representing a variety of industries. And over the next 90 minutes, regardless of your industry or your location, we're confident that you'll find today's webinar of value. Before we get started, Richard Fisher, publisher from Inside GNSS and Inside Unmanned Systems, would like to take a moment to welcome you and introduce our moderator as well as our sponsor for today. Over to you, Richard.
Lori, thank you. As always, on behalf of Inside GNSS, Inside Unmanned Systems, and today's sponsor, who is Spirent Communications, I extend a warm welcome to our audience from around the world for day 2 of our virtual workshop on autonomous vehicle safety. We're delighted you could be with us today again. Now, I'd like to introduce Ajay Vemuru. He's the product manager of PNT at Spirent Communications for some opening remarks. Ajay, welcome.
Thank you, Richard. And welcome everyone for joining today's webinar. And welcome back if you were attending yesterday's webinar as well. You may know Spirent as a GNSS simulator provider. This is something we've done for over 30 years and remains at the heart of what we do today. No one supplies more GNSS signals than Spirent. What you may not know is that in addition to our products, we provide test and evaluation services, and not just limited to GNSS. Increasingly, GNSS is used alongside other sensors and signals, and yesterday's talk did take you through some of our sensor simulations. Spirent supplies test and evaluation solutions that provide coherent emulation of whatever combination of signals and sensors are required. To do so, we work with industry leaders across the sectors to provide integrated solutions. Our aim is to provide solutions to PNT test challenges that are realistic and support multiple signals and sensors. We do this from internal development and through partnering with industry leaders. With that said, let's dive into today's webinar. Back to you, Richard.
Ajay, thanks a lot. Very interesting introduction. Now I'd like to introduce our moderator again for today's virtual workshop, day 2. Alan Cameron is the editor-in-chief of Inside GNSS, and he's the PNT editor for Inside Unmanned Systems. He's covered the GNSS, PNT, and autonomous markets as a writer and editor since 2000, focusing on technical issues around continuous, reliable positioning and navigation. Alan, good morning. Welcome.
And we're back to burn for a second day on this history-making initiative virtual workshop. Autonomous vehicle safety, how to test and how to ensure. We had a bang-up day yesterday, and we're here for more and deeper. We're going to go deeper into simulation, how to test for autonomous safety, and we're going to take a close-up look at the standards that are existing and developing for autonomous vehicle safety. We'll hear from Ajay again. We'll hear from Ali Soliman at Spirent and from Lance de Groot at Hexagon. First up, and of course we'll hear from you. We'll have your questions midway through the presentations and more questions at the conclusion of all 3 presentations, questions and answers. We'll get to Ajay's presentation in just a minute, but first, Lori, let's have a little input from the audience.
Let's do that. So on the screen there, first of our polls for today, what type of testing are you most familiar with? So I've got 3 options there on the screen to choose from: live sky, simulation, record, and playback. So it looks like we have 34% coming in with live sky, 43% simulation, and 23% record and playback. Alan, any thoughts here?
Well, the good news is we're going to be talking about all three of these. Ajay and Ali are going to take us through the contrast and compare, so to speak, because really all three are needed, and each brings a different strength to the testing scenario. But it's good to know that we have a somewhat even distribution of familiarity across the audience. Let's dive right into it. And we'll start with Ajay. Ajay Vemuru is Product Line Manager for PNT at Spirent Communications. He has more than 10 years of experience as a navigation engineer and has worked on various aspects of GNSS receivers, from research and development to integration and testing. He got his master's degree in electrical engineering and computer science from Ohio University. As I said, he's currently a Product Line Manager at Spirent Communications, helping the robotics community build safer and more reliable location-aware platforms. Before starting at Spirent, Ajay worked as a software engineer and research engineer at two of the leading semiconductor companies in Silicon Valley in California. And after a successful career researching advanced location algorithms and developing software towards improving location-based services on mobile devices, he's now responsible for launching new solutions targeted towards automotive and the robotics market. Ajay, take it away.
Thank you for the introduction, Alan. All right, so software development in automotive sector generally follows the V process. You can notice the picture on the right-hand side with two sides of the V, where OEMs take responsibility of the requirement specification, system design, integration, and acceptance tests. This is typically followed by the supplier who develops the actual code that runs on the ECUs. Although the code is tested at the supplier level, the OEMs are subsequently responsible for the final integration system and acceptance testing to ensure that the given implementation of the software meets its intended functional and safety goals. The system and integration tests are all conducted in a hardware-in-the-loop setup. Hereafter, I refer to any hardware-in-the-loop setup as HIL setups or HIL rigs. The HIL systems are designed to include a number of fully integrated software packages that allow controller software to be validated using manual and automated methods. In HIL system, a software model executing in real time replaces the vehicle for which the control unit under test is designed. A simplified architecture of the hardware in the loop can be seen on the left-hand side of the slide here. The real-time model emulates the vehicle system sensor properties, the buses that exist in the car or in the vehicle, and sometimes also pre-processes any actuator signals. It actually is the behavior of this control system under fault conditions. Now, if you remember yesterday, we did talk about the various faults that can be injected. So it's those fault conditions under which the system has to be evaluated. And this is really key. And in particular, that system should exhibit some kind of a deterministic behavior. So you understand that for these set of specified faults that you are injecting, you understand the behavior, you fix them, you try to isolate them, and then you repeat it, then see how the performance has changed. Yeah, to enable these failure modes to be set during each automated test, a fault injection unit is used, and as you can see on the plot, there is a fault injection block, which for our purposes is essentially a PNT simulation system. So what do we have here? Here is the setup of our vehicle sensor simulation in a HIL environment. Again, HIL is hardware in the loop for short. The simulator simulates all sensors, including GNSS, IMU, wheel takes, and any or every other vehicle sensor. The input to this simulator is a real-time 6 degree of freedom trajectory information that comes from a vehicle model from the previous slide, if you can relate this. Spirent does not believe in reinventing the wheel, and hence we're working with top-of-the-class vehicle modeling companies that provide realistic motion models and trajectories as input. We also have made sure to consider to be compatible with almost the industry standard hardware platforms that are running real-time operating systems. This motion model is converted into RF signal for GNSS and is converted and is translated or mapped onto a CAN bus for other sensors and sent to either the ECU or a GNSS receiver. Now, if you note that from our previous V diagram that we had on the previous slide, that HIL comes just before the final vehicle level test or pre-production level testing, which does involve having a vehicle in the loop, which does get expensive. And you want to simulate the test environment in HIL with as much realism as possible to rule out any fundamental issues in the system before transitioning into the vehicle in the loop setup. So back to this setup here, as an option, we also offer a realistic multipath simulation capability to add the richness, to add the realism of the overall HIL rig. And Ali will be talking about the multipath simulation capability and ray tracing later on today. So who needs HIL setups? So predominantly OEMs who want to test with realistic vehicle models can integrate GNSS or PNT in a bigger HIL rig. As you might have picked up already, each HIL rig represents a single vehicle. In similar fashion, Tier 1s can also test in HIL environment by including relevant ECUs in the loop, but with a more generic vehicle model rather than a very specific vehicle model that the OEMs use for their testing. HIL setups are gaining momentum in all industries, including UAV, aviation, and space. As you can imagine, the core of the system needs to be with low latency. And Spirent is known to provide industry-leading simulators with lowest system latency overall. With that said about HIL, we think that the audience here will also be interested in understanding a bit more of how we can enhance PNT performance in a real vehicle-in-the-loop system. This is where tapping into the sensor connectors becomes critical to mock relevant sensor inputs. You can see this on the slide here on how the rolling road is going to contribute as one of the inputs. So it in turn generates the wheel takes, and we can pick up on that information, and we can create and we can simulate coherent IMU and GNSS with that input data. So with that said, thanks for listening. I'll hand it back to Alan so we can continue through the rest of the presentations.
Thanks, Ajay, for that introduction. We're going to proceed now deeper into the testing and simulation with Ali Soliman, Business Development Manager for GNSS and PNT Technologies and Automotive Vehicle Testing Systems at Spirent Communications. Ali received a Bachelor's of Engineering honors degree in Electronics and Communications from Brunel University, London, and a master's degree in Telecommunications with Business at University College, London. He started his career at Spirent as a hardware engineer and since has held multiple positions, including Solutions Engineer and Product Manager. He's currently leading the business development for the Americas, focusing on defining complex solutions and helping customers solve their test needs with Spirent's current and future portfolio of products and services. He's an all-round technology enthusiast with a particular interest in PNT, connected and autonomous vehicles, and artificial intelligence. Ali, please proceed.
Thank you, Alan, and hello, everyone. I would like to start by highlighting the different testing approaches that are available: live sky, simulation, and record and playback. You may be tempted to take what looks like the simplest and most cost-effective approach using the available satellite signals in the sky. This type of live sky testing generally entails capturing the overhead signals via an antenna on the roof and rebroadcasting them on the factory floor. However, as this slide shows, this approach has issues and limitations that seriously compromise the accuracy and efficiency of the functional test. With a simulation, the test engineer can be sure of applying exactly the same conditions and test parameters to every device coming off the production line, for example, as well as ensuring the repeatability and the control. A simulator can also be used to generate signals from constellations that are not available in the sky above the factory, either because they serve different parts of the world or because they are not yet fully operational. As was highlighted yesterday, the only practical method of assuring autonomous vehicle safety is by injecting as many faults as possible and capturing as many corner cases as we could think of. Simulation enables that. Record and playback systems are good compromise between the live sky and simulation. This is because it is the next best realistic method of testing after live sky, while providing a good level of repeatability, but it lacks the level of control necessary for a good test coverage. It also lacks the availability of reference truth that is required to help you benchmark your performance against the known data. Truth data can be obtained while using RPS systems. To do that, you will need an external device, for example, the NovAtel span receiver. The three different approaches discussed are complementary to each other and are needed at some part of the development and qualification cycle. This V model highlights the different stages of development of autonomous vehicle. At each stage, different GNSS test approach will be necessary. For example, in the early stages of the development, where only model-based testing is necessary, a software-only simulator may be necessary to test for that particular model within the system. As the development matures, different approaches will be necessary. For example, simulation will be necessary during the system integration and hardware-in-the-loop testing, as Ajay just highlighted. The final level of the validation stage will involve all three approaches of testing, including live sky. With a credible and realistic simulation, live sky testing will be minimized. I would like to highlight again this boundary diagram concept that Groot showed in yesterday's session. Clearly, there are many faults that has to be considered. It was highlighted also yesterday by Lance that the only practical way to do such tests for a complete test coverage, including corner cases, is using simulation. GNSS simulations gives you the ability to manipulate all parameters in the three different segments of any GNSS constellation. Spirent GNSS simulator provide the ability to test many of the relevant errors directly using the internal models, or even indirectly by manipulating the constellation and the signal parameters, for example, the signal power level, code, or carrier phase. Let's break the testing to basic and advanced level testing. Basic testing like time to first fix and position accuracy may appear unnecessary as those parameters are stated on the supplier datasheet, but it is also important to test for those because many errors and performance issues are introduced post-integration. For example, what is your actual TTFF after integrating the antenna to the solution and then integrating the positioning solution within the vehicle alongside all the other systems that may affect the weak GNSS signal? It is therefore important to test even the basic parameters. Advanced testing covers corner cases and focuses on application-specific testing, for example, multipath and obscuration in urban environment, and other signal vulnerabilities, which I will cover in more details in the third session. Advanced testing also covers compliance testing, which Lance will cover in the next session. So like with any test equipment, there has to be good level of confidence in the test kit to ensure the credibility of the testing. This is particularly more relevant for safety critical application where human lives are at stake. When choosing your GNSS simulator, there are multiple factors to consider. First, does your simulator support the latest interface control document or ICD? Some new signals and updated ICDs are not even live yet. A credible simulator should have any latest ICD implemented as soon as they are released. Another factors to consider are the hardware update rate or simulation iteration rate and the corresponding fidelity and accuracy of your simulator. Especially in corner cases and hardware in the loop environment, it is essential that the hardware is optimized to the GNSS signal to ensure maximum control over the overall system timing and performance. This is when using specific hardware and FPGA design for GNSS is much more beneficial than the over-the-shelf SDRs. Scalability is another factor that need to be considered. Can your simulator scale to more frequencies and constellation as your test need increase? And most importantly, does this scalability compromise the performance? Other factors to consider is how easy it is to integrate the simulator within your automation tool, as well as is your simulator calibrated against a known standard like the ISO 17025. Finally, I would like to highlight realism. This is important to give your testing the necessary credibility and assurance that what you are testing with is indicative of real life. There are different aspects that could be considered when considering the realism of your testing. First one I would like to highlight is atmospheric effect. It is essential that a GNSS simulator is able to replicate to a degree the level of errors in the signal as a result of either ionosphere or troposphere or even scintillation. It is also important that you have the ability to define those errors in the simulator to replicate a particular test case or behavior seen in the field. The next aspect of realism is environmental effects surrounding the vehicle. This could be buildings, traffic signs, or even pedestrian. I will discuss this in more details in the third session. Let's now look at the other approach to testing, the record and playback system, or I will refer to it as RPS. So how do you iterate, design, and test GNSS urban environment performance realistically, but also repeatably in the lab? RPS is the answer. The way an RPS works is that it samples the RF analog signal and converts it to a digital IQ data that is stored on a storage device like an SSD. During playback, the digital IQ data is converted back to analog and outputted to your device under test with the same level and fidelity that was captured in the field. As well as GNSS signal, an RPS system could record other signals of opportunities, as I will show in the next slide. There are multiple factors to consider to ensure your RPS system is up for the job. The first of those is the quantization level during the sampling process. Higher quantization level not only ensure that the signal will be captured with the highest fidelity, which is important for precise positioning application, but also it ensures that the dynamic range of the system is high enough to capture both the GNSS signal and any surrounding interference or even strong fading in the signal in deep urban environment. 4-bit I and 4-bit Q is the minimum quantization level we recommend, but 8-bit for each, the I and Q is also important to ensure that a signal is captured in all cases, especially in deep urban scenarios. Next factor is the clock stability and possible added phase noise. The majority of high precision systems rely on both the code and carrier phase of the signal to compute a precise solution. A record and playback system should capture the signal and replay with as little added phase noise as possible. Another important factor is the availability of large storage for your record and playback system. As you see in this table, just over 1 hour of recording for 8-bit 2 frequencies uses about 1 terabyte of storage. So it's essential to ensure your RPS system supports the necessary internal and external storage as to not to limit the test duration. Finally, a record and playback system should capture more than just GNSS to ensure good test coverage. As Groot highlighted yesterday, there are more than just GNSS that is used in the positioning engine. When you go out in the field for a test drive and record the data, you will be aiming to record all those signals that drives the positioning engine. GNSS, of course, is a must, and it may be that you even want to record for multiple antennas. Correction data is another important input, as we heard yesterday. The GNSS 6450 allows you to record both RTK serial messages or PPP data over Ntrip server. You may also want to capture your CAN or CAN-FD data, which will include the dead reckoning sensors and maybe even additional IMU. And finally, you may want to record other IMU outputs as a reference, or even a video camera capture of the surrounding. The most important point to make here is that your record and playback system should allow you to record and replay all of those signals in sync with GNSS signal without the need for any additional tools or synchronization. This concludes the first session. I will now hand over to Alan.
Thanks, Ali. We'll be returning to Ali for a further presentation a little bit later in the program. Right now, we're going to go to Lance de Groot from NovAtel, who's going to talk about safety standards. Lance is Senior Team Lead for Geomatics Software Safety Critical Systems at NovAtel Inc., part of Hexagon's Autonomy and Positioning Division. He holds a bachelor's and master's degree in science in geomatics engineering from the University of Calgary. He joined Hexagon NovAtel in 2008, and during his tenure he's worked on many cutting-edge technology projects, including developing algorithms for ground reference receivers used in SBOS networks, high-precision positioning and relative alignment algorithms for commercial applications. His current focus is developing safety-critical software for autonomous applications, so he's well-versed in these standards. As I said, he's Senior Team Lead for safety-critical systems at NovAtel. Lance, let's hear all about these standards.
Thank you, Alan, and hello, everyone. So on this slide here, I'm showing the three main standards I will talk about today. There are a few others that may be relevant depending on your industry. For example, if you're working in truck and bus, then perhaps IEC 61508 is more applicable than 26262. And there are some other organizations who are looking at safety critical applications for GNSS in general, such as RTCM and 3GPP. And of course, NHTSA has the V2V standard. But I'm going to focus on these top three because I think they're the most relevant for this audience and this topic. So the main standard that you will see people talk about and implement is ISO 26262. This is the specialization of IEC 61508 for series production passenger vehicles, so anything up to 3,500 kilograms. And its goal is to address hazards that are caused by malfunctions of the electrical and electronic systems inside the vehicle. And it defines a process model and objectives to minimize those faults and account for those faults through system, hardware, software development, verification, and a number of supporting processes. So I cannot cover the entire standard in 10 minutes, but I will take us through a quick tour and hit a few of the highlights. The first major process step is the concept phase. And in this phase, the first thing you do is identify the function of what your system needs to achieve, and then you do a hazard analysis and risk assessment, the HARA. And here you analyze possible hazardous events, possible faults that could affect your system, and what the outcome of those is, and you classify them based on their severity and the likelihood they are to occur. And then you define safety goals to address these hazards. So if you were here yesterday, you saw Gord mention that autonomous driving systems are ASIL-D. Let's run through a quick example to show how we arrive at that. Take, for example, your hazardous event is unintended steering traveling at freeway speeds, which of course could lead to a collision, possibly even crossing a center line. So the severity of that is life-threatening, the highest severity class. A collision at high speed is always going to be life-threatening. The exposure is the highest class because there's a high probability. And this is the high probability that you will be in a scenario. So the chance that you're driving on a freeway. It is not the probability of the fault itself. This is the probability of the condition that leads to the hazard. And the controllability is the highest rating, which is uncontrollable. And this is controllability by the driver, not by the systems. And so because we're talking about a fully autonomous system, the driver is not going to be controlling it. They may not be paying attention. And so it gets the highest rating. And so based on those ratings, that's how we arrive at the conclusion that autonomous driving systems will be ASIL D, which is the highest rating. So you do this for all of the possible hazards in your system. You define safety goals to address these, and then you come up with a functional safety concept. And this is where you start thinking about how are you going to actually achieve those safety goals? What features are you going to put in your system that will mitigate against them to make up for the fact that the driver can't control them? So you think about things like the fault-tolerant time interval. How long can your system still perform after a fault occurs? Do you have any sort of degraded operation, or do you immediately fail? What are the safe states of your system? How do you transition to them? What other systems are available to operate when you're in a safe state, and so on. Then we move into the system design phase. The system design phase, you decompose your functional safety concept into a technical safety concept where you allocate those requirements to your architecture. You start identifying specifically where you're going to implement these safety functions. Then you proceed with the rest of your design. Your safety requirements get included with all of the performance and functional requirements that you'll have. You work that design all together, and you'll perform a safety validation. And the tools for this would typically be FMEA, FTA, DFA, dependent fault analysis, which in automotive, you'll be doing these anyway, especially FMEA. The difference here is that your focus now is on failures that lead to a violation of the safety goals. A classical automotive FMEA may be more focused on reliability concerns, but with the 26262 safety analysis, you're really focused on the safety consequences of failures in your system. You then move on to hardware and software. If I could go back a slide, actually. So there's two sub-Vs in the 26262V model showing that hardware and software occur simultaneously. On the hardware side, again, you do the safety development along with the rest of your development. You have hardware safety requirements decomposed from the system safety requirements that you work with the rest of your design. The big change that the standard brings here is the hardware metrics. This comes from the FMEDA, Failure Modes and Effects Diagnostics Analysis. And this is essentially a very comprehensive calculation of how each individual component in your system, its rate of failure, and what that failure will do. And so you can add up the total failure rate of your system, and you can understand at the component and subcomponent level how all of these individual failure rates contribute. And you get a bunch of metrics out of this, how resilient your system is to single point faults or dual point faults, what the safety considerations are of latent faults, or the overall failure rate, which is FIT, failure in time. And you can see in this table, the higher the ASIL rating, the higher the metrics that you have to achieve, because your system is more hazardous, or I guess is the hazards of your system are more consequential, and so you have a higher burden to make sure that those hazards don't occur. On the software side, it's a similar story. The development is fairly similar to any other structured software. You'll do requirements-based design, architecture, detailed design. 26262 recommends various design principles, such as having hierarchical structure, loose coupling, high cohesion, use complexity metrics to make sure that you have low complexity in your software, and so on. It calls for you to use suitable coding standards, and two very popular standards here are MISRA-C or MISRA-C++. These aren't the only ones you can use, but these are very popular. They were originally developed for the motor industry, and they have also seen adoption outside this industry since then. And then the standard calls for you to do unit and integration testing with the goal of achieving requirements coverage as well as structural coverage. And like with hardware, the rigor needing to be reached for the structural coverage increases with the higher ASIL rating of your system. So at A and B, you're looking at statement coverage, branch coverage. By ASIL D, you're trying to achieve full MCDC coverage. And I just want to talk a bit about verification. It's in the supporting processes section of the standard, and that's because the standard is a V model. Verification happens throughout. As you descend and climb up each of those Vs, there's verification activities occurring. And so the verification really focuses on robust testing methods, and there's a few examples on this slide from some of the recommendations from the standard. And you can see there's stuff like error guessing, fault injection, resource usage. So it's not calling for a fairly direct requirements-based pass-to-fail approach. It really is encouraging you to do more comprehensive, more robust testing, trying to exercise those failure conditions, test to fail, make sure your system is robust and it handles in an appropriate way when these conditions occur. And then the last note here about testing I want to make is the standard requires confidence in your tools. If the tools you're using to generate or analyze data fail, that can lead you to misinterpret the data, and it can cause you to have failures in your system. So you have to have an analysis of your tools similar to the HARA. You consider how likely they are to lead to failures, and how likely it is that any failures in your tools would be noticed elsewhere in the process. And then you assign a tool confidence level to each of your tools, and that imposes standards and requirements that your tools have to meet. So that's all I have about 26262. We'll break here for some Q&A, and I'll come back and talk about SOTIF afterwards. But for now, back to you, Alan.
Thanks, Lance. Quick question for you about that last slide and ISO 26262. Is following ISO 26262 mandated by any regulatory body?
Not by a regulatory body. There's no standards that say that you cannot sell a vehicle if you don't apply this standard. But it is considered the state-of-the-art for safety-critical development in automotive. And so from a legal perspective, a liability perspective, following 26262 is the de facto standard. If you're doing your due diligence in developing these systems, you should be following this. And you would have a difficult argument to make if you had a liability and you chose not to follow this standard.
Right, right. Ajay, reaching back to your presentation, how was Realism or Sim3D as a solution validated?
Right. Okay. So Sim3D, as with any of our product line, does go through a rigorous test and validation process internally. And beyond that, what we have done is we have collected some sample data points from the field, reproduce the same scenario in a simulated environment with Sim3D, with all the ray tracing happening, and we try to correlate and see, or maybe even tweak further on how good Sim3D is. So that's how we kind of came up with the framework, and we are using that framework going forward to make sure that there is good bit of alignment between field test and Sim3D.
And another question for you, Ajay, obviously from an antenna expert in the audience. In your simulations, do you assume a perfect antenna, or how do you account for less than perfect signal input from the antenna? For an example, an antenna with very poor PCV on an azimuth or elevation angle basis.
Right, that's a good question. So as you would expect in simulations, you start off with everything being perfect, right? But that doesn't mean that is where we stop. So we take our simulations to the next level by giving users the flexibility to modify anything and everything that we simulate, includes the antenna. So users will be able to change the antenna patterns, or they can also add a realistic antenna pattern into the solution and include that in the pipeline of their validation.
It's good to know that you have that. You provide that flexibility. Ali, a question for you. Can a record and playback system play back the CAN data on a live bus?
Yes, absolutely. The Spirent GNSS 6450 can be used with active CAN or even CAN FD bus. The system deals with all the necessary arbitration and handshaking, as well as message filtering, for example, to ensure no data collision is happening on the CAN bus. So this is definitely a possible use case, yes.
Further on the simulator capabilities, can the Spirent simulator do both interference and spoofing in one scenario? I know that's a challenging situation that hopefully no one will ever have to encounter, but it's quite possible. Can you simulate that?
Yes, this is a really good question, and the answer is yes. And I will show some further capabilities in the third session on this. Spirent does provide multiple capabilities. One of them is the embedded interference with multi-vehicle, one RF. So you could have multiple vehicles, each having a specific trajectory. One is your DUT and one is your spoofer. And both features could be combined in one scenario and orchestrated by the user and all outputted on one RF to your device under test. So the short answer is yes, and I will cover some of that in the third session.
All right. Resuming from Lance very shortly, and Ali will be back for the third session following that. And following that, we'll have more questions, plenty of time for more questions from the audience. And you have your panel there to input them. As I said, we have at least one antenna expert in the audience, and we've had a question already from that source. I can see that we also have a representative of a major U.S. car manufacturer sitting in the audience, as we did yesterday, who posed some very pressing questions. It's good to see that that interest in autonomous vehicles is widespread and going to the very top of the supply chain. Big wheels keep on turning. Lori, let's have another poll from our audience.
Okay, let's do that. On your screen, you should see that second poll question, experimentally validating the performance of safety critical autonomous vehicle PNT system will require. Go ahead and select one of these, a month's worth of data, a year's worth of data, 10 years worth of data, can all be done in simulation. All right, just 7% of our audience weighing in with a month's worth of data, 28% a year's worth of data, 29% 10 years worth of data, and 37% can all be done in simulation. Alan, what do you think?
Well, I am not going to venture an opinion here because I'm going to kick it to our panelists. This $64,000 question, can it all be done in simulation, or do we need data as well? With that open question lingering in the air, back to Lance for more on safety standards, and then following Lance, we'll hear from Ali again. Lance, go ahead.
Thanks, Alan. I won't address that question right away, but I do have one slide that may tie in a little bit. So if we look at SOTIF, with the other main standard I want to talk about, this is designed as a supplement to 26262. And the reason for this is that ISO 26262 really focuses on the hazards and failures, or hazards that come from failures of the E&E systems inside the vehicle itself. It is not concerned about any external failures. But obviously for us in this industry, if we have GNSS signals, we have as well cameras, LiDARs, other sensors coming into this, external factors are a major impact. And that's where SOTIF comes in. It focuses on hazards that can occur even if the system itself is completely fault-free. There are other hazards that can occur externally, and that's what we have to deal with. So it's thinking about things like limitations in the function. For example, if you're using AI for feature classification, that AI is going to be limited. It won't be right all the time. Or errors in the external inputs, which for us in GNSS is very relevant because we do have all of these error sources. So you can think of 26262 is safety of execution. Did you actually build the system safely based on what you think it should do? And SOTIF is safety of performance. Will it actually work safely? Have you thought about it and designed it correctly? So this figure on the bottom here is from the SOTIF standard. And it kind of summarizes the concept of what they're trying to achieve. Sections 2 and 3 on this this region here are the known unsafe and the unknown unsafe conditions that your system can experience, and 1 and 4 are the known and unknown safe conditions. So the goal of SOTIF, the goal of the analysis, is to try and minimize as much as possible those known and unknown safe conditions so that as much of the time you're in safe operation. So SOTIF is tied into the 26262 process model. It calls for additional activities occurring at various steps. And one of the main ones up front is you do a hazard analysis very similar to the HARA in 26262. The difference in SOTIF is that you have to consider different triggering events. So you consider the environmental conditions as a possible trigger. So for example, if you're using a camera to observe the lines on the road, but the road is covered in snow, or if you're using a camera for feature recognition, but you have rain mist on your camera, Those are very plausible environmental conditions, and you have to think about how those affect your system. You think about the limitations of your system components, so the resolution of a LiDAR or so on. Foreseeable misuse. If you have a front-facing radar and someone puts a grill cover on the vehicle, what does that do to your signal? Can your system handle it appropriately? Those sorts of things. Then, like with the HARA, the 26262 HARA, you assess the events by severity and controllability, so you can see which ones are acceptable and which ones are not. Any risk that is unacceptable, you modify your design to reduce the impact of that risk. So you could improve the performance of your sensors, choose cameras with higher resolution, LiDAR with a faster scan rate. You can restrict the operating environment. So for example, only allowing a feature to be used on a divided highway if the risk of crossing the center line is too severe. You can add additional monitoring or fallback, more sensors, more redundant systems if you need to, or you can improve testability. So if you can better observe a possible failure through verification, you can be more sure that it's not going to get into the series production product. And then the other main part that SOTIF talks about is the verification and validation process. So all of your test design also has to consider these SOTIF-style risks, the external factors, the misuse. So you have to consider and design test cases that will stimulate some of the same things that you thought about in your hazard analysis. And then at the end of your verification process, SOTIF calls for you to evaluate the residual risk of your system. And there's a number of different methods recommended for that. Randomized HIL-SIL testing. You can do large-scale fleet tests. You can do simulation. And so the HIL-SIL and the simulation get to the topics that Ajay and Ali have been talking about. You can also have support for this through analysis. And as I talked yesterday with the fault tree analysis for GNSS integrity, this can be a way through SOTIF we can analyze the residual risk of our system. So just to touch back to Alan's question, can it all be done in simulation? My opinion is probably not, and SOTIF is looking for you to use a mix of different methods to evaluate your residual risk, but definitely having that simulation there to support a little bit of live driving can really help to ensure that you really characterize that residual risk properly and are catching these boundary conditions. So the last standard I want to touch on quickly is EN 16803. This is under development in Europe, and it's a standard that is trying to cover assessment of GNSS-based positioning systems in intelligent transportation. So it's still under development. Only the first part has been released. The first part covers defining metrics that will be used to characterize positioning systems. Parts 2 and 3 will define requirements and classifications for basic and security performance respectively. And the fourth section of the standard will define some methods and some processes for verifying GNSS-based positioning systems. So only the first part's been released. I think it's yet to be seen how impactful this standard will be. But I wanted to bring it up because, to my knowledge, this is the only standard that is really specifically driving at the verification side of GNSS technology in autonomous driving and intelligent transportation systems, whereas the other standards are really more on the development side. So this is potentially an important missing piece. And with that, I will hand it back to Alan to go on.
Thanks, Lance, and thanks for answering that question. We can see that as elsewhere in life, diversity is a good thing. You have some simulation, you have some live sky testing, some record and playback. It's good to approach with a broad spectrum of solutions. We're going to return to Ali now. Yesterday, we had a lot of interest in Multipath as part of the scenario, the environment. And Ali, I understand you have some Multipath content to present with us first. So let's have it.
Thank you, Alan, and hello again. So let me start by highlighting that there are many errors that affect the GNSS signals. Multipath and obscuration is one of them. In fact, multipath and obscuration is a major contributor of error in GNSS measurement, especially in urban environment. This phenomenon causes multiple copies of the signal to reach the receiver, a direct and a reflected signal. The reflected signal will take a longer path and will be delayed relative to the line of sight. Shadowing or obscuration effect will also cause major error in GNSS measurement. This happens when the satellite line of sight is obscured by an object surrounding the antenna. Over the years, GNSS simulation was limited to statistical modeling for multipath. Those statistical models provided some value, but limited value, if I'm honest, and did not provide the necessary realism to add credibility to the testing. One way to increase realism in our simulation is by using a virtual 3D world simulator. These simulators must have 3 engines to add real value to our test setup: the environment engine, the physics engine, and the solver. It is the interaction between these engines which adds realism to our test. The environment engine is the 3D world itself, for example, the building, the vegetations, the traffic signs, and even the terrain. It also includes the material assigned to each of those objects. And of course, all the moving objects are part of our simulation, but not necessarily directly related with our device under test. For example, the pedestrians, the traffics, and even animals. The physics engine is usually a set of equations that tells the virtual 3D world simulator how to interact with the environment. For example, in a GNSS simulator, the physics engine contains the signal properties for each satellite. Also, it knows how these signals interact with the environment. Basically, how they are reflected, diffracted, or even transmitted when they encounter different objects and materials. It also contains the propagation model, which say how the signal are propagated in space. And finally, we have the solver. We need to discretize our equations and solve them in a fixed or variable step size. In a GNSS simulation, for example, we need to discretize the simulation time and signals themselves. Nowadays, it would be really expensive for a computer to solve how a spherical signal or even light propagation would interact with the environment. That's why the industry uses techniques such as ray tracing or path tracing to simplify the infinite continuous wave front into a set of rays that we can then handle and simulate at RF. For Spirent, these 3 engines have one solution, SIM3D. In collaboration with Octal SE, Spirent has introduced SIM3D, which combines the 3 engines we have talked about to add value by bringing real-time multipath and obscuration effect to the GNSS signal. SIM3D enables the user to test under different 3D environments for both static and dynamic scenarios. All interactions between the signal and the surrounding environment is taken into consideration and then simulated on the RF signal. SIM3D promises an indicative performance to those seen in the field relative to the environment being simulated. SIM3D is one of those optional tools that can help you achieve realism in the test setup. You can see here 2 examples about how SIM3D could be used. The white lines are the line of sight coming from the satellite. Those are the signals coming directly from the satellite. The red and blue lines are reflections and diffractions of the rays. When they are interacting with the environment. As they interact with the environment, you see the diffraction and reflections. A tool like SIM3D takes into account the vehicle 3D model as well, so the user is able to import their own vehicle 3D model to the environment. It would have been impossible for such use case to be achieved with that level of realism without having SIM3D. Let me now focus a bit on GNSS antenna. And GNSS antenna is an important factor in the performance of the overall positioning engine. And over the year, there has been many advancements in antenna technologies that could support sub-meter accuracy, but this doesn't necessarily mean that those advanced antennas are suitable for production level automotive. There are many factors in play, and in particular cost, of course. In the early stages of development, testing your solution with a representative antenna is not possible. simulation should provide a level of antenna testing enough to represent the real performance. There are many factors a simulator should take into account. For example, the antenna pattern. It's important to test with a representative antenna pattern for both the gain and phase. It's also important to highlight that the final antenna pattern will change once the antenna is integrated in the vehicle. Other factors a simulator should factor for is the antenna polarization and even the placement of the antenna relative to the vehicle. One approach I would like to highlight when testing the complete system, including the antenna, is over-the-air zone chamber approach. And this is different to the typical over-the-air approach where only one single antenna is used to radiate all the signals from one direction of arrival. In this new approach, which is patented by Spirent, the sky is divided to different zones with each zone having their own azimuth and elevation boundaries. The signal is transmitted from the right direction of arrival, and this allows the testing of the complete solution while ensuring the antenna own gain and phase pattern is used without the need for modeling in the simulation. Sim3D can also be used in the zone chamber environment. We even ensure that the multipath signal for each line of sight is radiated from the correct direction of arrival. This ensures that the best realism possible for a complete solution is achieved. So let's now look at spoofing and interference. Spoofing was once extremely hard to do, but recent demonstrations have shown it is now easy to build a GNSS spoofer from open source software and low-cost components. False location and time reading can have severe impact on the autonomous vehicle. Anti-spoofing capabilities are improving, but so are the spoofing techniques and sophistication. It is essential to test for spoofing attacks and ensure appropriate flags are raised when a spoofing signal is received. Important key parameters to consider when simulating spoofing is the signal fidelity of the spoof signal and access to a dedicated spoofing tool and scenarios to help you orchestrate a repeatable, successful spoofing attack. Spirent have multiple capabilities that enable testing for spoofing attacks. For example, simulating up to 12 copies of a single constellation. Each constellation will have their own, you will be able to have full manipulation over the parameter of each constellation. For example, the orbital data, the signal properties, or any additional error. Spirent also provide the ability to simulate multiple vehicles, each with a specific trajectory. One vehicle will act as a DUT and another will be your spoofer. Finally, Spirent offer a dedicated software called SimSafe that enables the user to orchestrate a spoofing test scenario. Different type of spoofing levels are offered with SimSafe. For example, data and signal spoofing level, as well as meaning. It's also worth highlighting that with SimSafe, SimSafe allows the possibility to align the spoofed simulated signal with the GNSS live signal. Jamming attacks aim at denying the reception of the genuine GNSS signal by overshadowing them with noisy waveforms. This can saturate the receiver front-end antenna, even when pre-filtering for out-of-band interference is used. The jamming waveforms are typically several dBs more powerful than the GNSS signal, which are anyway hidden below the thermal noise floor. So although GNSS receivers are equipped with an AGC circuit to prevent saturation of their ADC, this has a limited dynamic output range and can therefore decrease the amplitude of the incoming jamming signal up to a certain degree. In addition, under strong jamming condition, typical civilian GNSS receivers will be unable to look accurately to the code of the GNSS signal and decode the navigation message. Therefore, they may provide a degraded navigation solution or even no output at all. The graph on the top right corner of the screen shows the number of interference incidents reported by pilots over the last couple of decades. Clearly, you can see a steady increase in the number of especially in the last couple of years. This is because access to jamming devices is becoming quite easy. Key parameters to consider for interference simulation is the need to simulate not just one interference source but multiple. Those could be static or dynamic interference sources. Also, it is important to realistically model the power between the jamming source and the DUT, especially in a dynamic scenario. Spirent does offer multiple interference simulation capabilities. The first solution I would like to highlight is the embedded interference. This allows the use of the simulator to simulate simultaneously the GNSS interference signal from the same simulator. Up to 8 N-band interference sources could be simulated, each with a realistic power modeling and precise phase alignment. Different interference types could also be simulated, for example, CW signal, PSK, and AWGN signal. The next capability I would like to highlight is the GSS 7765 interference simulation system. This comprises one or more high-quality commercial signal generator plus an interference combiner unit. Up to plus 10 dBm of output power could be simulated with broad range of interference signals options for both in-band and out-of-band interference. Okay, this concludes session 3 of this webinar. Thank you all for listening. I would like to hand over now to Alan.
Thanks very much, Ali. We're going to get to some questions, to audience questions in just a moment. But right now, we're going to ask you a question, audience. What are you most interested in testing for?
Yes, it should be up on your screen at this moment. Responses, as you can see on the screen. Basic system performance, sensitivity, accuracy, TTFF, etc. Performance under spoofing and or jamming conditions, standards compliance, ISO 26262, SOTIF, etc. Or all of the above are equally important. Okay, it looks like 20% coming in with basic system performance, sensitivity, accuracy, TTFF, etc. We've got 24% coming in with performance under spoofing and or jamming conditions, 11% with standards compliance, and 45% feeling like all of the above are equally important. Any thoughts here, Alan?
Well, of course, all of the above is the safe answer. It covers all your variants, all your aspects. First among equals, spoofing and jamming. I think that's well reflected in all the conferences I've been to recently over the past 3, 4, 5 years. Basic system performance, close behind. Standards compliance, that's perhaps a little bit further down the line in just in concerns perhaps of the audience in terms of fielding products. You want to nail your performance under spoofing and jamming and basic sensitivity and accuracy, and then before you actually take the product to the field, you better be sure that you have your standards right. We're going to turn now to questions from the audience, questions for our panel. Ali, I'm going to go to you first with 2 questions have come in about the 6450, its capabilities. The first, someone wants to know what's the sensitivity of the 6450. How low a signal can be recorded on the 6450?
Thank you, Alan. Yeah, this is really a good question. And the GNSS 6450 can capture the GNSS signal at the noise floor, including any deep fading in the signal. If used with, especially if used with high bit depth, as I highlighted in the slides. Any signal above the noise floor by a couple of dBs will also be recorded. We do recommend using an active antenna to overcome the unit own noise figure. Spirent GNSS 6450 also has an AGC to ensure that the signal level recorded is then played back at almost the same level when captured in the field. So I hope this answered the question.
Yeah, I hope so. I believe so. Second question about the 6450, can it manage, record and replace several vehicles for multi-vehicle applications?
Yes. So the short answer is yes, this is possible. So as I mentioned, a single 6450 can record 2 antennas inputs. Most likely, those 2 antennas will be on the same vehicle. But what we can also do is synchronize multiple GNSS 6450 systems together to record more antennas and more signal, all in sync. The level of synchronization achieved is to a few nanoseconds. This allows a much advanced configuration, of course. It's also important to highlight that the 6450 can be triggered to start recording on a particular GPS 1 PPS signal. The unit itself has an internal receiver that could be used. So this is significant for recording from multiple sources physically apart.
All right. Lance, a couple of questions for you. First, can you, since we're talking about multiple systems, can you describe a little bit further how multiple systems can be combined to meet an ASIL-D objective?
Sure. So as I showed in my slides, most autonomous driving functions are probably ASIL-D, but that's the rating for the function itself. The standard does allow you to decompose an ASIL-D safety requirement into requirements that are dealt with by multiple systems of lower ratings. So you can make up an ASIL-D with 2 ASIL-B requirements, or with an ASIL-A and an ASIL-C, and an ASIL-C in turn can be further decomposed into an A and a B, and so on. So you can do that, and that's a way that you can leverage redundancy between systems to not have to design every system to the very strict standards of ASIL-D. The trick is you do have to prove that there is sufficient independence between them. You can't just drop down 2 identical ASIL-B GNSS receivers and say that you now have an ASIL-D GNSS function, because they'll be vulnerable to the same faults. They do have to be designed independently. You have to be able to prove there's no common cause errors that will affect them. But then if you can do that, then you can build up a system that will reach a higher rating.
All right, coming back to you again, Lance, with a question about cybersecurity. Is there any standard to follow for cybersecurity in regards to safety?
Sure. Specifically for automotive, there's a couple that you're probably interested in. The one that has been around is SAE J3061, which was published a few years ago. And just this year, a draft came out of the ISO Automotive Cybersecurity Standard, which is ISO 21434. And that's actually joint with SAE. It builds on 3061 and should replace it, but it's still in draft. The first draft was just published earlier this year.
Okay. Ali, how tight is the synchronization? Someone wants to know, how tight is synchronization across GNSS and other data recording?
Yeah, this is a really good question and very important. For the GNSS 6450 record and playback system, we ensure the synchronization between all signals is within a few nanoseconds. We also it's also important to highlight we use a single reliable OCXO, oven-controlled crystal oscillator, to sample all the data and record them with the GNSS. In fact, Spirent hold a patent for recording serial data and storing it in the GNSS IQ file without impacting the C over node of the recorded GNSS signal. So I believe, yeah, the synchronization level that we can achieve is very suitable for the majority of the applications out there.
Another question involving synchronization. In a spoofing scenario, what's the level of synchronization between the live and the simulated signal that could be achieved?
Yeah, the level of timing synchronization between the live signal and simulated spoof signal is in the range of 50 to 100 nanosecond. So this is achieved by synchronizing our simulator 1 PPS and 10 megahertz clock with a reference receiver. We also, it's worth highlighting that it's not just the timing that we synchronize with, we also ensure that the broadcast ephemeris of the simulated data is updated to reflect that live data.
Okay. Lance, regarding SOTIF, you mentioned that it adds foreseeable misuse. One fairly obviously fairly knowledgeable audience member asks, is this not already required to be considered in ISO 262 HERA? Is the SOTIF standard also considered state-of-the-art and therefore de facto required for road vehicles?
Sure. So for the first part, yes, the questioner is correct. 26262 does also identify foreseeable misuse in the HARA. And I think this speaks to there's a lot of overlap in general between 26262 and SOTIF, especially in terms of the design analysis. So for me, I think having that in there twice encourages you to think about misuse in the two different contexts. Because 26262 is more focused on failures of the system itself, you may only be thinking about misuse of those systems as opposed to misuse of those systems in the context of the wider world. One of the examples given in the 26262 standard of misuse is adjusting your seat while you're driving, which is really still focused on the systems internal to the vehicle. Whereas in SOTIF, if you're in the mindset that you're thinking about the external factors, that may bring different misuse scenarios to mind, or it may not. It may be that through your 26262 HARA, you identify the misuse scenarios fully, and that would be fantastic. To the second part, SOTIF was only released last year, so it may be too early to say if it's a de facto standard yet, although it is explicitly identified as an extension of 26262, which has been considered as such. I'm not a lawyer, so I don't think I can provide definitive advice on that topic, but I think it's definitely worth watching.
Thanks, Lance. Ali, is there a pre-prepared scenario or recording for multipath spoofing interference that could be used to validate a receiver without in-depth expertise in the subject matter?
Yes, this is something Spirent is able to provide, and we do appreciate the difficulties in generating a successful spoofing scenarios or even representative multipath environment. So Spirent has ready scenarios that the user can just drop in their simulator, or even a recording that they can just drop in the record and playback system to test quickly their device under test. Those scenarios also come with reference truth, so it is easy for the user to obviously compare the result they are getting from their DUT with the truth data. In fact, we can even test for you in our lab, or you can come to our lab and use our equipment to test yourself. I'm happy to provide more details on all of this. If anyone interested, please get in touch.
Okay. Lance, a question for you about the length of time covered by the standards. You have the question in front of you. I wonder if you could read it aloud, please, and then answer it.
Sure. So the question is there a requirement to operate auto drive for a defined length of time to prove safety of use? And the answer is that there is nothing defined in the standards. And in fact, the standards don't define specifically what the required integrity risk or failure rate for such a system would be. 26262 does set out targets for the hardware failure rate, but if we're thinking more in the SOTIF context of the failure rate of the function, and then at the end assessing that residual risk, there are no hard targets given in the standard, and so there can be no clearly defined test methodology to prove that you've met them. And so I think you'll see different OEMs, different tier ones will adopt different approaches to this based on trying to meet or to exceed the incident rate or the fatality rate of human drivers as targets, and they'll have their own approaches in how to prove that they've achieved these.
And one final question for Ali. According to the boundary scan diagram, is it possible to insert faults by the user to simulation?
Yes, this is possible. In fact, Spirent Simulator provide many internal models and turnkey features to test such faults. We also provide, as I mentioned, ready scenarios to help you quickly test, but you also have the ability to inject your own error and faults. You have the ability to inject your own solder range errors, your own code and carrier phase errors, and you could have also the ability to change any of the constellation 3 segments parameters. So even the upload data from the ground segment, for example, you have the ability to change that up to each navigation bit. So we give the user full control over the constellation.
All right. Thank you very much. Well, it's been an informative webinar for myself. I have to say, even though I've gone through the material a few times with our panelists, each time I get a little more out of it. And I want to tell the audience that you too will have the opportunity to experience the webinar again and absorb all the details. It will be made available to you to replay and also to share with colleagues, and it will be recapped very briefly in a future issue of Inside GNSS Magazine. I want to thank everyone for attending. I want to thank our panelists, Ajay, Ali, and Lance. I want to thank our sponsor for today, Spirent Communications. And we'll go around the room, go around the virtual panel with closing comments from each of our panelists. Ajay, last message for the audience?
Those were some interesting questions. Thank you for listening in. I just want to conclude by saying at Spirent, we are really motivated to aid the development process of PNT to achieve autonomy by providing the right tools. So let's work together to accelerate the development. Thank you.
Yes, and an exciting future in autonomous development awaits us all. Lance, closing comment from you?
Thanks everyone for listening. I think as an industry, we definitely have a challenge ahead of us to develop these systems to meet these challenging targets. And I think from the questions we got, it's clear that our audience is very engaged and very informed, and it's good to see.
It is good to see. Ali, final words from you.
Yeah, thank you all for attending, and I hope you find the material useful for both days. And and feel free to get in touch with any thoughts or questions that you may have. Thank you again.
All right. One final round of thanks for our 3 panelists, Ajay, Ali, and Lance, and also extending one to Gordon Heidinger, who was part of our panel yesterday. It's been a very informative 2 days, very in-depth, technical, professional, virtual learning experience. We're glad to be able to provide this kind of training during these challenging times, during any time. That's what we're here for. Thanks again from Richard Fisher and myself at Inside GNSS. And Lori, back to you.
Thank you. And just most importantly, thank you for joining us. This is Lori Dearman saying, hope we see you on the next one. Bye for now.